Welcome back! In the previous video lectures we have used a Sankey diagram to visualize the flow and conversion of energy carriers of the energy system of the European Union in the year of 2023. We will use this Sankey diagram to construct an energy balance for the energy system of the European Union. Energy balances are an excellent tool to analyze the total energy supply and demand of a country or a region, to analyze the region's energy security, analyze the economic efficiency of the energy system, analyze the progress of climate goals, and support policy decisions by providing a comprehensive, comparable view for past, current, and future energy systems from production to the consumption by the sectors. It's a crucial tool for planning, assessing data quality, and managing the transition to sustainable energy. The learning objectives of this section is to learn how to read and use an energy balance for a certain region or country and how to construct such energy balance. As discussed in the previous video lectures, the Sankey diagram of the energy system of the European Union includes all total primary energy sources available and the conversion of a primary energy carrier into a secondary energy carrier and the distribution of the total final consumption in the different sectors. For a country or region, an energy balance is typically presented as a matrix as shown here for the European Union. It is the equivalent of the Sankey diagram. The energy balances are compiled for all countries annually by the International Energy Agency in cooperation with the United Nations. Now let's run you through the process of setting up such an energy balance. I first start relatively simple. I only consider the total primary energy source gas, how much gas is available, how this energy carrier is converted into secondary energy carriers like electricity and heat, and how the gas is finally consumed in the various sectors. Here you see a simplified energy balance. In this energy balance, every column represents an energy carrier. For the example of following the value chain of gas, we consider the primary energy carrier gas and the secondary energy carriers like electricity and heat. As you can see, the table has three sections. These sections represent the total primary energy sources available, the conversion into other secondary energy carriers including conversion and distribution losses, and the total final energy consumption. The upper section, indicated in green, summarizes the amount of total primary energy sources available. This primary energy is made available through the winning or production of primary energy carriers, the import of primary energy carriers from outside into the region considered in the energy balance, minus the export of the primary energy source outside that region. The rows in this section represent production, import, and export respectively. The middle section represents the conversion of primary energy carriers into other secondary energy carriers, including conversion and distribution losses. The rows in this section represent the conversion plants. Like for gas, this is a gas-powered electricity plant, or gas-powered combined heat and power plant, and or a district heating system. An additional row at the bottom of this section represents distribution losses and or energy consumption by the energy industry sector itself. The third section in the table represents the consumption of gas in the various sectors. The rows represent the sectors for which gas consumption is relevant, being the industry, the residential sector, other final consumers, and non-energy use respectively. As energy gas is irrelevant for the transport sector, I have not included it here. Let's start with production, import, and export, which are represented in the three rows, and the columns represent the primary energy sources gas and the secondary energy carriers electricity and heat. Considering only the gas energy flow in the equivalent Sankey diagram, it means we have to focus on the left part of the Sankey diagram. The shown number scale with the width of the arrows and is proportional to the amount of energy distributed, converted or consumed. It is expressed in the unit megatons all equivalent, abbreviated with MTOE. It shows that 22 megatons all equivalent of gas is produced in the European Union. This shows as a plus 22 in the production row and gas column in the energy balance. Additionally, it shows that 299 megatons all equivalent of gas is imported into the European Union. In the matrix, this is shown as a plus 299 in the production row and the gas column. Finally, it shows that 54 megatons all equivalent of gas is exported out of the European Union region. In the matrix, this is shown as a minus 54 in the export row and gas column. This means that total primary energy sources gas available is the production plus import minus export and makes for the European Union in 2023 a total of 267 megatons all equivalent. The last column adds up all primary energy sources available, and as in this example we are only considering gas, the numbers in the total column are equal to those in the gas column. Let's move to the conversion of the primary energy carrier gas into the secondary energy carriers. Or in other words, the middle section of the matrix that makes the energy balance. If you consider again the energy value chain for gas within the European Union's energy system, conversions and losses are visualized by this part. The red arrow indicates the 34 megatons all equivalent of chemical energy in gas, which is utilized to generate electricity in electricity plants. As the gas is being consumed, this ends up as minus 34 megatons all equivalent in the electricity plant row and gas column. Another 42 megatons all equivalent of chemical energy in gas, indicated by the red arrow, is utilized to power combined heat and power plants. As the gas is being consumed, this ends up as minus 42 megatons all equivalent in the combined heat and power plant row and gas column. And a small fraction equal to 8 megatons all equivalent of chemical energy in gas, indicated again by the red arrow, is utilized to power district heating. As the gas is being consumed, this ends up as minus 8 megatons all equivalent in the district heating row and gas column. An even smaller fraction of 4 megatons all equivalent in gas, indicated by the red arrow again on the right, is lost in its distribution. These losses refer to natural gas that disappears from the network before reaching the customer, primarily due to leaks from aging pipes, faulty equipment, or third-party damage. As it represents a loss, the sign in front of the number is again minus. At the electricity plant, 50% of the chemical energy contained in the 34 megatons all equivalent is converted into electrical energy. As indicated by the red arrow, this is 17 megatons all equivalent electrical energy. As it concerns generation, this is shown by plus 17 in the electricity plant row and the electricity column. In the combined heat and power plant, another 17 megatons all equivalent of electricity is generated as indicated by the red arrow. Again, as the electricity is generated, this is shown by plus 17 megatons all equivalent in the combined heat and power plant row and electricity column. In addition, the combined heat and power plants generate about 11 megatons all equivalent of heat as indicated by the red arrow. As the heat is generated, this is shown by plus 11 megatons all equivalent in the combined heat and power plant row and heat column. For district heating, 6 megatons all equivalent heat energy is as indicated by the red arrow. Again, as this heat is generated, it is shown by plus 6 in the district heating row and heat column. If you consider the electricity plant only 50% of the chemical energy contained in the 34 megatons all equivalent is converted into electrical energy, implies that another 70 megatons all equivalent of chemical energy in the gas is lost in the conversion into electricity. The conversion losses of the electricity plant is represented in the total column, shown by minus 17 megatons all equivalent. It is the sum of the row, the gas plus electricity plus heat, thus minus 34 plus 17 makes minus 17 megatons all equivalent. If we consider the combined heat and power plant, only 68% of the chemical energy contained in the 34 megatons all equivalent of gas is converted into either electricity or heat, which means the other 14 megatons all equivalent of the original chemical energy in the gas is lost in the conversion. The conversion losses of the combined heat and power plants is represented in the total column minus 14 megatons all equivalent. It is the sum again of the row gas plus electricity plus heat, thus minus 42 plus 17 plus 11 is equal to minus 14 megatons all equivalent. If we consider the district heating, 6 megatons all equivalent in the form of heat is converted out of 8 megatons all equivalent in the form of gas, which implies that another 2 megatons all equivalent of original chemical energy in the gas is lost in the conversion. The conversion losses of the district heating is represented in the total column, minus 2 megatons all equivalent. It is again the sum of the row of the gas plus electricity plus heat, thus minus 8 plus 6 makes minus 2. The total secondary energy source in the form of electricity generated is 34 megatons all equivalent. This electricity will be available for final consumption in one of the sectors. The total secondary energy source in the form of heat that is generated is 17 megatons all equivalent. This heat will be available for the final consumption in one of the sectors as well. The total primary energy source in the form of gas, which is still available for the total final consumption, is the initial amount of primary energy source minus the gas used in the plants, minus the distribution losses, minus the use in the energy industry itself. In this example, 179 megatons all equivalent in the form of gas is available for the total final consumption as well. The total final consumption, gas, electricity and heat, this row is highlighted in green, is coming from and or converted out of the original total primary energy in the form of gas, which is 230 megatons all equivalent. It is the total primary energy source minus all losses. The last section of the matrix to complete the energy balance is the consumption by sectors. The total final consumption is now the top row of this section. If you consider again the entire gas value chain in the Sankey diagram, the consumption of the sectors is shown on the right, together with the distribution losses we have already discussed. The industry in the European Union consumed in 2023 a total of 67 megatons all equivalent in the form of gas. It shows as plus 67 in the industry row and gas column. You would think, as this gas is consumed, it would make sense to use a minus here. Yes, you are right. However, in many balances in this specific section, the consumption is considered to be positive. The residential sector in the European Union consumed in 2023 a total of 68 megatons all equivalent in the form of gas. It shows as plus 68 in the residential row and gas column. The residential sector in the European Union consumed in 2023 a total of 68 megatons all equivalent in the form of gas. It shows as plus 68 in the residential row and gas column. The same is valid for the other final consumers with 38 megatons all equivalent consumption and the non-energy use with a 10 megatons all equivalent consumption. And now we have constructed, using this Sankey diagram, the energy balance related to the energy carrier gas. Production, import and exports determined the total primary energy source available. Some gas has been converted into electricity and heat, including the conversion and distribution losses, to the final consumption in the sectors. This simplified energy balance only includes one primary energy carrier and two secondary energy carriers like electricity and heat, and does not reflect the entire energy system. In the second part, we will construct the entire energy balance representing the energy infrastructure of the European Union. See you in the next video.